Dear SBFT 2023 participants, my name is Dmytro Humeniuk and I am a PhD candidate at Polytechnique Montreal under the supervision of Professor Foutse, Khomh and Giuliano Antoniol. And today we would like to present our submission to the SBFT 2023 tool competition of the Cyber-Physical Systems track, which is named the RIGAA. And RIGAA tool stands for Reinforcement Learning Informed Evolutionary Search for Autonomous Systems Testing. And in this presentation I will talk about why we decided to use reinforcement learning, how we use it, and our approach in general. I would like to start by presenting the problem that we were solving in this competition, which is testing an autonomous vehicle lane keep and assist system in a BMG simulator. To test the system, we need to produce valid and challenging road topologies defined as a sequence of points. And by saying valid, I mean the road topologies that do not go out of the bounds, are not too sharp, and are not self-intersecting. Typically, this problem is solved by running some search algorithms which promote road topologies that make the vehicle deviate from the road center as much as possible. However, one of the problems is that running the simulation-based evaluation of test scenarios is computationally expensive and takes non-negligible amount of time. It is commonly known that a good initialization is important for a search algorithm. Good initialization can direct the search in more promising regions of the search space and reduce the time spent on evaluating non-promising scenarios. In our approach, we suggest to perform an intelligent initialization of the search algorithm by producing some percentage of the initial population with a pre-trained RL agent and the rest of the population with a random generator. Experimentally, we fixed this ratio to 40 to 60, meaning 40% produced with RL agent and 60 randomly. RL agent is pre-trained to produce test scenarios that have high diversity and also better fitness than those produced randomly. And then some sort of search algorithm, for example evolutionary search, can run, and the best scenarios produced can be then selected for the final test suite. To train an RL agent, we define the problem of generating a test scenario such as a road topology as a Markov decision process. At each step, the agent selects one of the possible actions, such as adding a straight road segment, adding a road segment turning right, or a road segment turning left. Agent also selects the values described in the segment, such as the length of the straight road segment or the turning angle. Then we evaluate the test scenario with a simplified kinematic model of a vehicle, which is based on known equations defining vehicle kinematic movement. And we do not use expensive simulators such as BMG to evaluate the test scenario produced by an agent after each episode, as it would be computationally expensive. On the left, you can see an example of a test scenario receiving high reward, and on the right, example of a test scenario receiving a low reward. So intuitively, scenarios receiving low reward should be less challenging for the vehicle. Now I would like to discuss the performance of the trained RL agent as well as the performance of our approach RIGAA. When comparing RL agent and random test scenario generator, RL agent is able to produce around 65% fitter scenarios, and we evaluated the fitness based on the performance of the lane keep and assist system in a BMG simulator by measuring its deviation from the center of the road lane. And we can see that RL agent is outperforming random generator, which means that the simplified model based on vehicle kinematics was actually useful for training and guiding the agent. And in the future we also plan to look into other simplified models such as surrogate models based on Bayesian optimization. And next, we also compared the number of failures revealed with NSJ2 with random initialization and NSJ2 with RL-based initialization, which is our RIGAA approach. And we could see that RIGAA found around 24% more failures than NSJ2 with random initialization, while keeping the same level of diversity of the solutions. You can see that sparseness of failures did not have a statistically significant difference. As a conclusion, I would like to say that combination of reinforcement learning based on initialization and genetic algorithm is beneficial, and our approach could actually achieve the second place in the cyber-physical systems testing competition. However, in the future we plan to work further on improving the reward function in order to produce more diverse scenarios and more fit scenarios by improving the feedback we give, maybe by using more accurate surrogate models. Finally, we also plan to explore other possibilities to combine machine learning and genetic algorithms, for example, by using machine learning for fitness prediction or crossover, selection, mutation operators. Finally, I will be very grateful for you for any questions or feedback on our work, and you can reach out to me via my email. I'll be very happy to answer them. Thank you very much for your attention.